Okay, so welcome everybody to our 49th episode of the SFU Sports Analytics Virtual Seminar Series. It's my pleasure today to host Dr. Michael McBride from the University of California at Irvine, who's going to talk to us about team production in baseball using the Shapley value to assign credit for offensive performance. So Dr. McBride is a professor of economics in the School of Social Sciences at the University of California, Irvine, and he's the founding director of the Experimental Social Science Laboratory. He received BA and MA degrees from the University of Southern California and Masters of Philosophy and PhD degrees from Yale University. His research uses game theory and experimental methods to study conflict, cooperation, and strategic interaction. His baseball research uses concepts from coalitional game theory to create new baseball statistics that identify each player's fair share of credit for producing runs or outs. He has also published two books that help youth baseball and softball coaches apply key concepts from sabermetrics. In terms of his talk today, the project that he'll speak about uses the Shapley value from the coalitional game theory to create new measures of offensive performance in baseball. His presentation will introduce the new statistics, and describe their calculation. It will also review what the data reveal about current and past baseball players. And with that, I'm going to hand it over to Dr. McBride, and welcome to our seminar series.
All right. Thank you very, very much for letting me share this work with you today. It's exciting to be able to share this with a new audience. And as an economist, I should let you know that when we give presentations, we're really rude with each other. We just jump in with comments. So, if you have a comment and you send it to Dave, I don't mind it, being interrupted. I'm kind of used to it. That's just the way we economists roll. Okay, so what's the motivation for this project? Well, when people get together and work together in teams and produce something, sometimes it's really hard to identify how the credit for the team's output should be fairly distributed among the different people who contributed to the team's output. And that's because there are a lot of production interdependencies. So it's hard to disentangle exactly how much one person's contribution mattered for the team's output when the output is measured at a team level. Now, this problem is one that goes back in economics many, many years. And my approach, and of course in sports, this is very important because so many sports are extremely interdependent. Players come together, they contribute, they do different things. There's some team output they share in, but how do we really divide up the credit for their contributions? So this idea and this concern goes back many years in economics, and there's actually an idea that goes back to the 1950s called the Shapley value, which I'm going to talk about today. And this is a concept from a discipline called coalitional game theory. And so I'm going to present today the first application of the Shapley value to measure individuals' contributions to team output in baseball. And this might be a bit surprising. Number one, because Lloyd Shapley, the guy who created the idea, was a huge baseball fan, and he never thought of this. So that's kind of interesting. Number two, team sports are an obvious place where there are production interdependencies, and we have lots of data. And so it might be kind of surprising that the Shapley value has not really been used a lot in sports. It has had a few applications in soccer, but they were very, 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 very different from what I'm doing today. And so there are three main contributions from this work. And so these contributions, I kind of put them under this title. I call them the fair credit baseball statistics, and you'll see why I call them that. But there are three kinds of contributions. There are conceptual contributions. I'm going to devise a way to represent offensive production in the sport of baseball as a coalitional game in the formal sense of coalitional game theory. And this is valuable because the Shapley value is derived from various fairness axioms. So I'm going to produce new statistics that satisfy fairness axioms, and no other baseball statistics can have this claim. There are some technical contributions. So there's going to be one key technical hurdle that has to be overcome. And I'm going to do this in a very particular way, and this is going to, in the end, involve some machine learning. So there's sort of some non-trivial computational elements to this. And then finally, of course, the payoff is, okay, what do the stats tell us? Okay? And so they're going to provide, in the end, a new and improved fair accounting of of people's contributions towards their team's offensive performance. And these are going to be measured in runs and win units. I'll have new leaderboards. I'll talk about MVP awards. So hopefully there'll be something for everyone by the end. Now, a really important distinction needs to be made right from the start. And that's between measuring skill, or really I should say accurately estimating skill, and accurately accounting for credit. So a lot of times in sports, we're really interested in estimating skill. We want to know who's the best player, how is this player going to perform in the future? Because I want to know the best players by my projections of players' skill, so I can construct my roster, I can design my lineup, whatever it is you want to do. But the idea is there's some underlying true talent a player has that's not observed, and so it has to be estimated. And so in baseball, I've given here several skill statistics. Batting average is a really old one that's been super popular. It's been surpassed by a lot of other acronyms here in the baseball sabermetric lexicon. Now, this is very different from accurately assigning credit. Credit is backward looking. It's saying I don't care about who the best player is. I just want to know for what happened on the field or on the court or on the pitch. I want to know whose contributions were most important that day. Okay, so it's not about projecting future performance. It's just about accurately accounting for what just happened in the past. And a lot of times in baseball in particular, sometimes the least skilled player might be the player that deserves the most credit. So this is a different kind of exercise. Now, the exercise I'm doing, it's about measuring credit. It's about assigning credit. It's not about projecting skill. Now, of course, it could be used in ways to help enhance skill measures, but really the fundamental motivation here is providing an accurate estimation of production in terms of credit. So let me show you what the stats can do. So this is a box score this is just a regular old baseball game from 2021 when the Arizona Diamondbacks defeated the San Diego Padres 3-1. So if you look at a box score on ESPN or some other outlet, this is supposed to summarize the game and tell a kind of story about the game. And if you look at this, we know they won 3-1. 3 runs were scored by the Diamondbacks. This is the Diamondbacks box score, where the first 3 players in the lineup are the players who are credited with those runs. These are players who literally crossed home plate. But there's another player who batted in a couple of those players. So if we were to look at this, it's not sort of obvious how the credit for the runs that scored in this game should be allocated. It's also not clear which of these runs were really most important for the win. They won by a score of 3-1. Which players deserve the most credit for outscoring the opponent? The offense's job is to outscore the opposing team. How should this credit be allocated? So when you look at and there's even a funny thing here. 3 runs scored, but only 2 are credited with being batted in. So it's really, there's something odd going on here. How do we know how to divide this credit? Well, these are the 2 stats I'm going to be sharing with you today. The first one is called a Shapley run credit. And this says of the 3 runs that scored, this is exactly the fair way to distribute credit for these runs. Peralta, the 4th batter in the lineup, deserves credit for 1 1/3 run of the 3. And the rest is distributed in this way. So this is for the runs. Now for outscoring the opponent by winning the game, there's 1 win credit that the team gets to divide up for the offensive portion of outscoring the opponent. And this is how the stat says, this is the fair way of distributing the credit for that. Even though Peralta gets credit for helping the team score the most runs, Peralta and Marte, actually, their contributions were equally important to outscoring the opponent. Okay. So that's what this tells you. So this is what the stats are going to be doing. So I'm going to be describing how these kind of calculations are made and give a little bit of the justification for it, and then show you what we can get from these. But this is a first application of these stats. This is going to enhance a box score if it was included. You just have to, if you have any contacts at ESPN, you let me know so I can convince them to add this to their box score. This is enhancing the understanding of what happened in the game. Okay, so what's the Shapley value? Well, it comes from 1953. Okay, this is well before even I was born. The basic idea behind the Shapley value is that value should be tied to the amount of the increase in production that the team makes when I'm added to the team. Okay. And so what this MI term, this is the marginal increase in the team's output, the team's value of player I, when added to some coalition S. Okay. But the problem is, when I'm added to the team, the marginal value I create for that team depends on when I'm added to the team. So there's a lot of ways we could add the team together. And what Shapley said was, what we need to do is we need to think about all the different orders in which players can be added to the team, find their marginal value across all of these, and then take the average. And that's literally what the Shapley value is. It's this average of the marginal contributions across all the possible orderings. And what Shapley proved, and this is one of the reasons why he won a Nobel Prize in economics several years ago, and because this idea has lots of applications in business and law and now in sports, is that this is the only way of dividing credit that satisfies a bunch of important properties. It's efficient. It's going to divide all the credit so no credit is left out. It's symmetric in that people are going to receive identical credit if they made identical contributions. It has this anonymity property, which means that only the contributions matter. It's not your name, your background, your parentage, anything. It's just your contributions. Marginalism, it's actually tied to the value you add to the project. And a nice thing is that it's unique. And so in this context, when applied to baseball, I'm gonna apply this concept in a couple different ways. One is the production of runs, and the other is the production of wins. So when I'm talking about the production of runs, there's going to be what's called a value function, which is where this M term is going to come from. It's going to come from a value function that has to be properly defined according to the dictates of coalitional game theory. And once we do that, then we can calculate this Shapley value. So let me show you in a very simple example how this is done. This is the first inning of that baseball game we looked at. There were 6 players who batted in that inning. Okay, now it turns out we're going to ignore the first and the last 2. These are what are called null players. They actually added no value, so we can ignore them without affecting the calculation. And focusing on a 3-player example is more tractable, okay? So let's focus on these 3 players. These are the 3 players in the team. These are the 3 players that produce runs. Now, there's lots of different ways that these players can be combined, okay? Now, and these 8 coalitions is the power set of the possible ways these players can be combined. One possibility is we have none of them. One possibility is we have just Marte, just Walker, just Peralta, and then we have 3 different ways of having 2 of them, and one way of having all 3. This is the full complete set of all the different coalitions. I have these abbreviations here. And these numbers over here constitute what in coalitional game theory is called a value function. And in this sense, because it's measuring runs produced by coalitions, it's called a run value function. Notice I've highlighted 4 of these. In the course of the game, what we actually observed were the run values in the highlighted ones. So before Marte batted, there was nobody in the coalition. Of course, nobody's batted. So no runs scored. No offensive plays means no runs scored. Okay. If just Marte bats, just after Marte batted, we had a walk. Now in baseball, a walk means the runner gets to base, but they haven't scored yet. So if we just have that offensive event, we have no run score. Now next we had Walker, Marte and Walker. Walker got a single. This is another runner getting on base. Now we have 2 runners on base. No one has scored yet. So just the 2 of them, we have no runs scored. Finally, when we add Peralta's triple, which scores those 2 runners, but he himself doesn't score. So the coalition with all 3, we have 2 runs scored. Now, this is what we observed in the game. So we know these run values. What we don't know are these other run values. So what we're going to have to do is we're going to have to use some baseball judgment. We're going to have to do some scorekeeping and conjecture what would have happened if in the hypothetical case of just these single events, Walker or Peralta alone, or these 2 pairs of events combined. Now, common baseball wisdom would give you these numbers here. So for example, if Walker gets a single, gets on base, but nothing else happens, there's no runs. Or if Walker gets a single and then a triple scores him, that's 1 run. Okay, so it's common baseball sense that these numbers should be this. Okay, but it is a conjecture. It's a hypothetical reconstruction of what that inning would look like with just these events. But this is how we're going to construct a run value function. Once we have the run value function, now it's just a simple calculation to get the Shapley value. So for example, one way of adding players to the coalition is adding Marte first, then Walker, then Peralta. If we add Marte first, before he's added, there's nobody in the coalition. So it's the none coalition, which is this 0. That's the value before he's added. After he's added, he's the only one in the coalition, which is the M coalition. But that also has value 0. So when we add Marte in this order, the marginal runs is 0. When we add him in this order, he's added third. Before he's added, WP are already in here. The WP coalition has value 1. When he's added, the value is 2. There's a marginal increase of 1 run. So if we just take all the orders, get all the marginal runs, we take the average, that's the Shapley value. And so this is where the Shapley value of 0.5 comes for Marte for that inning. Now, there's two big steps just to summarize. The first thing is we've got to construct the value function. This is how we measure what the output is for all of these coalitions, including the ones we observed, but also the ones we didn't observe in the data. And then second, we just do this calculation. Now, the second step is trivial with a computer, okay? For a small example like this one, I can do it by hand. For larger ones, it's just trivial for a computer. There's existing algorithms. It's no problem. Now, but this first step, this is where all the work is, because it's not always obvious how to construct these numbers for those coalitions that were not observed in the data. So there's two big challenges that I have to overcome. The first one is, okay, what are these hypothetical runs scored by coalitions that are not observed in the data? So conceptually, I'm going to redefine each play event. Here's how I'm going to do it. I have a table on the next screen to show you. I'm going to replace each play, not by the play event, but something I call a trigger, which is going to be a transition function, which is going to tell you how the state of the game when that event happens is going to be changed for any possible state that the game may find itself in. So what we only observed was the movement from one state to another, but I need to define what happens for any possible initial state to any other state. Once we do that, then we can use our scorekeeping judgment to replace these play events with these, what I call triggers. And then for any coalition, all I have to do is sequence through the triggers for that coalition and then sum up the runs that scored. And then I've got the value for that coalition. And I can do this for any coalition. Once I've got all the triggers for all the events, I can do this and repeat this over and over again for all the innings in all the games and all the seasons and and so on. So what does this look like? So these are the triggers from that Arizona Diamondbacks first inning. So the columns represent the initial base, what are called in baseball base out states. So this 000-0 is nobody on third base, nobody on second base, nobody on first base, and nobody out. Over here, 110-1 is a runner on third, a runner on second, no runner on first, and 1 out. And the data in the row for this first batter, this ground out, these numbers tell us how from this initial state where it will transition to as a result of this person's play. Now, the green boxes trace out the path of play in the actual inning, okay? But what we need to do for a full trigger is I need to get all the remaining boxes in that row to have the entire row, and the entire row is this trigger. Because once I have the entire row, then I can pick different rows for different play events, combine them, and calculate through how many runs scored for a particular coalition. So that's what I've done here. I've taken the triggers for W and P, W single, P's triple. Now these occurred in this sequence in the real game, but in a hypothetical coalition, they would occur like this. In the real game, when they sequence, this 0 means 0 runs scored, 0 runs scored, 0 runs scored, 2 runs scored, 0 runs scored, 0 runs scored. So in the real game, 2 runs scored, But in this hypothetical coalition, only one run scored. So by combining the triggers, I can construct the value for this coalition. So, but I've just got to figure out what all these triggers are. Okay. Conceptually, now I know how I want to do it, but now I've got to figure out, well, how do I get these actual data? So then the next step is another challenge, because we have over 100 years of baseball games and there's millions of play events. And so this is too much for me to do by hand. So what I did was I manually, with a computer, with Python code, I coded the baseball judgment for triggers for hundreds of games. Okay, it took a lot of spare time just sitting in front of the TV, you're working late at night. And this is a kind of enhanced scorekeeping. It's as if I'm watching the game and I'm saying, this play, had it happened in these other, in another situation, another base out state, it would have led to these outcomes. Okay, now the next play. This would have led to these other outcomes, the next play. So doing this for a lot of games. And then I apply this code. By the way, I should say I got this data from retrosheet.org, which is a great resource for baseball researchers. The data are freely available for download, and I have to give them credit for this, because I need play-by-play data. I need data on each play as it happens. Now I've written this code. I've done it for hundreds of complete games. Now what I can do is run it for all the games, and it won't be able to code everything, because there will be some plays it doesn't know how to code, but it'll be able to code a lot of games. And to give you a sense of how many it could do, here's a graph that tells you how many plays I have per season from the retrosheet data. And what you see is in the last couple decades, we have about 200,000 plays per season. A much smaller fraction are the postseason games, the playoff games, okay? But this number, farther back you go in time, it's smaller, and that's because there were fewer teams, so fewer total games. And there was also there's some few dips due to labor strikes and the COVID pandemic, where they shortened the season. So there's a few blips, but in general, you have this increasing trend over time as the number of teams goes up. Over here in this figure, it shows you the total plays. And then these are, of those total plays, these are the plays that my code couldn't interpret. It just didn't know how to interpret them. And you can see it's about 200 a year. Now, if I were to go and try to manually code these, I wouldn't finish before I retired. I probably wouldn't finish before I died. So this is where the machine learning is going to come in, because I'm going to train the machine learning model to interpret all the plays, including the ones that I couldn't manually do myself. So I'm training the machine to be a scorekeeper, to do this enhanced scorekeeping, to judge plays as triggers, not just single play events. So we're going to take all the data where I could assign triggers. We're going to split that into training data and have testing data. I'm going to have 24 different decision tree classification models from the machine learning. I'm going to train for each, and these 24 correspond to the different initial states of the game. So for each initial state of the game, there's going to be a model for that particular state that's going to predict what would happen for this play for plays that happened in other hypothetical initial states they might come from. So 24 different models. This gives you a sense of the size of the training data. We're only going to train on the data where there are the predictions, not the actual states, because we're trying to train it to predict out of the actual states. And so the number of observations we have for each initial state varies based on the number of observations we have. The more observations we have of a state, the less we have to train in that state, because we're training out of the sample data. Once we do this, we can get a full set of triggers for all baseball history where there's a play-by-play game since 1916 to the present. This is what the decision tree classification model looks like for one particular instance. This is an initial state where there's a runner on first base, but no other runners and no outs, and the batter hits a double. So a double typically advances 2 bases, but a lot of other funny stuff can happen. And so these nodes in this tree correspond to the different variables we have in the machine learning model. These variables are created using the play description from the retrosheet data, which is a string of characters. And so these these nodes, based on these variables, the model will then trace out through the tree. And if we come down this process, it says, well, if this variable is 0, it's true, and this variable is 0, and this variable is 0, then this is going to be the predicted outcome. But if we go this way, we're going to get a different predicted outcome. So this is what the tree looks like. This is just part of one tree. The trees are huge, okay? So this is just to give you a sense of what these things look like. Okay, so how well does the model do? So this is the testing we did within the sample where we actually had the assigned triggers. We trained data and then we tested on the testing data. And this first column tells you for each of the 24 different models for the initial states, this tells you how many times out of 100,000 play events we mispredicted what the testing data said it should have been. So for out of every 100,000 plays, when there's nobody on and nobody out, nobody on base and nobody out, only 2.8 out of 100,000 plays were mispredicted. So we think that's a pretty good rate. As the initial state changes, the error rate changes. Generally speaking, the more runners you have on base and the fewer the outs, the more craziness can happen in a game. Errors happen, fielding errors happen. The runners have more bases that they can advance to. They can get thrown out and they can be put out in different locations. Weirdness happens. That makes those plays harder to judge. And those are also plays where it's more likely even two humans doing scorekeeping might disagree on how to judge it. And so the prediction rate is worse in those situations. Note, this doesn't mean that these are mistakes by the model, because it's also possible that the model is actually doing a good job here and it's finding inconsistencies in my own programming of the code. And so it's possible the machine is actually doing better than me in some of these situations, that its prediction is better than mine, more consistent at least. But we think this is a pretty good, so when I say I received good assistance from Robert McDonald, a graduate student who helped with the machine learning portion of this. Now for plays that have fielding errors, the misprediction rate is again much higher. And this is again a situation where there's a lot more judgment that has to be involved, and there's competing principles that you could use for doing the scorekeeping. What this part of the table says is this has to do with how long the play description is. So the longer the play description, the more complicated the play, and the more likely it is that there's going to be a misprediction. So that's what this, so don't worry too much about the details of that, but that's the basic sense. Okay, so when all that is said and done, what do we get? Well, what do we observe about this Shapley run credit statistic? What Shapley run credit is going to tell you is reflect how necessary each contribution for each player was to the run. The total SRC for a team is going to equal the total number of runs actually scored. It's going to capture any kind of contribution a player can make to offense, including things that are not recorded as runs or RBIs. So for example, you might have a player who does a bunt to move a runner over, advance them a base, and then they score on a later play. That would not be recorded as a run or an RBI, but yet that's a key play for that inning. That player would receive some run credit. For a home run in which a batter hits the ball over the fence and they bring themselves all the way home by themselves, they don't rely on anyone else to score them, they will get the full credit for their own run and their own RBI, but they're going to split the credit if there are other runners that were on base that they batted in. You can actually have negative SRC, which is interesting, because it might be that your event, given the events that happened before your event and the events that happened after, your event might have prevented runs from scoring. So this would be a negative SRC. What makes it really different is that it's a holistic measure. Any kind of offensive contribution, whether it's a batting in a runner, whether it's getting on base, whether it's advancing a runner, whether it's stealing a base, these are all captured and put into this one single measure. So it's a holistic measure. It's really the only holistic credit measure in baseball. Lastly, because of the Shapley value, because of its very structure, you can actually sum across games, series, seasons, and careers and maintain all the consistency in the measurement. So this is a nice feature. So if we look at the last baseball season, which just ended last month, during the regular season, this is a little leaderboard, and I've sorted by SRC. The two top players in Shapley run credit for the season were Shohei Ohtani and Aaron Judge. So if you don't know these names, that's okay. Shohei Ohtani is a Japanese phenom. Aaron Judge is probably the best hitter right now in the game. They were the top two. Now, this is interesting, these numbers, because historically, these are two of the best, most productive run seasons in Major League history. And so this is the single season leaderboard for Major League Baseball from 1916 to 2022. And if you were to stick Ohtani's output, he'd be right there. And you'd take Judge's output, you'd put him right there. So we just witnessed two historic seasons by baseball players in terms of run production. A lot of these other names you probably have never heard of, but many of these are who's list for baseball inner circle players, inner circle Hall of Fame players. Here's just to put it up. This is the career leaderboard. It's headlined by Barry Bonds, who's a player who played in the 90s and 2000s. He said that he's also the career leader in home runs. Hank Aaron, second in career home runs. So these are just among the best players that played the game. And so not a surprise that they are leading this career leaderboard. Don't get too bogged down in this. I just want to show you that this statistic, this Shapley run credits, positively correlated with other offensive statistics in baseball. The correlation with WOBA, this is a rate statistic, whereas SRC is a counting statistic. So we don't expect this correlation to be super strong. It's positive as we expect, but not super strong. These two measures, weighted runs created and run expectancy 24, these are two estimates of a player's contributions in total runs. And we see that the SRC is highly correlated, but there's different variants here that these things are that SRC is capturing. SRC is measuring run contributions game by game, adding up, whereas this measure here on the bottom left is an estimating it from seasonal stats. So obviously this is going to have different kind of smoothing going on. This measure is based on the expectancy of runs. So it's not actual run scoring, it's the expected runs that you're contributing to your team. So this is probabilistically based. And so not a surprise it's doing something different, because my stat is actually trying to distribute credit for the actual runs that scored. Okay, so that's SRC. What's OSWC? It's an awful acronym. I probably should have chosen something different. It stands for Offensive Shapley Win Credit. So what do you do in this? Instead of simulating just the inning, like we do for the run credit, we're going to simulate the whole game using all the play events for the players for that entire game. And we're going to see how many runs each coalition can score in that entire game. And if your coalition can score more runs than the other team scored, then that coalition has a win value of 1. Otherwise, they have a win value of 0. And this is how we construct the value function. So the intuition here is that to win a game, you need to outscore an opponent. It doesn't matter how many runs you outscore them by. All that matters is you outscore them. And so you're in the value function, your coalition will get credit if you just outscore the opponent. So what are some features of this stat? I'm not going to go through the calculation. Okay, you've already seen enough of that. Offensive Shapley win credit is going to be very positively correlated with the run credit, but not perfectly so. Interesting, because its calculation depends on the number of runs scored by the other team, the distribution of credit according to this Shapley calculation will depend on the number of runs scored by the other team. So in this game, so here are the Shapley run credits, the box score I already showed you. This column here with 3-1, this is the actual Shapley offensive Shapley win credits for that game. But if you can imagine that the Diamondbacks won the game by a score of 3-2 instead of 3-1, then in that case, they could not have won the game without the contribution of every player, because every player's run was necessary for them to outscore the opponent. In that situation, the Shapley value is going to equally split all the credit. Even though the players contributed different run amounts, each player was necessary, and the team could not have won without each player. So it's going to equally split the credit. As the score margin of victory increases, we see that the credit is going to be distributed more unequally. And so if it's a blowout win, now Peralta is going to get the lion's share of the credit because and in fact, one of the players, now their run contribution was never marginal, never marginally significant. So it was never valuable in winning the game. So this player no longer gets any win credit. So this is a feature of this, and it reveals just how context specific this statistic is. Because it's one win credit, it's going to divide one unit. And so we have this nice, efficient accounting. But just like the Shapley run credit, you can sum over series, seasons, and careers. So going back to 2024, if we sort by OSWC, now Aaron Judge is number one. Okay, so he's played for the New York Yankees, which is one of the most well-known teams. Shohei Ohtani played on the Dodgers, one of the other most well-known teams, the Dodgers of Los Angeles. This is also an interesting number because it is also historically one of the best ever. This is a single season leaderboard for OSWC, and Judge's 2024 amount is the 25th highest in history, which is phenomenal. Oddly enough, it's less than 2 years ago when he did even better. So he has 2 historic seasons in just a 3-year span. That's just phenomenal. Okay. This is a career leaderboard. Let me skip that. Okay. Here are some more correlations. So you can see that it's strongly correlated with the runs that's scored. So this is a correlation between Shapley run credit and the win credit. Here is the this is another rate statistic for batting skill, and this is positively correlated, but not so strongly as you'd expect. These are 2 different measures. This is a probabilistic measure of win contribution, so it's positively correlated. This is a measure of wins called wins above replacement, which captures both offense and defense, whereas my stat is just offense. They're correlated, but imperfectly so. Okay. Okay, so now let's get to the last application, then I'm done. Then we can chat. And I see there's some comments in the chat. I'm sorry I didn't notice that earlier, but I'll get to these as soon as I'm done here.
No problem. They're good questions for the end.
Yeah, I agree. Okay, so this one might be a little more interesting application. So I argue that this offensive Shapley win credit is the best statistic that we have to use when selecting the most valuable player award for a playoff series. Okay, so there's a couple things here. So why do I say playoff series? Generally speaking, in baseball, so there's a regular season MVP award. There are also MVP awards for specific best of 7 series in the playoffs. In the regular season, it's widely understood that the MVP doesn't go to the most valuable player in terms of what they actually contributed. Really, it goes to the best player. So in the regular season, it's really a best player award. Okay, but in the playoffs, that's not the case. In the playoffs, the idea is that the MVP award should go to the player who is believed to have helped their team the most to win the series. Okay. And it's also true that offensive contributions are generally weighed much more important than defensive contributions. And the main reasons for that is that on the big scheme of things, individual players on the defensive side of the field make relatively small contributions to the win. Pitchers make a lot, but individual field non-pitchers don't. And what offensive Shapley win credit, I even did the acronym. I even messed myself up here. OSWC, it provides the most accurate accounting of how much the offensive contributions actually mattered for the wins. So I argue this is the best measure of value that you can have for thinking about the playoff MVP. So the World Series ended just a couple weeks ago. And Freddie Freeman of the Los Angeles Dodgers was selected as the most valuable player. Now, this table, this first column is the OSWC each player on the Dodgers got for the entire series. And we can see that Freeman was the best. He deserved this award. Not only was he the most valuable as measured by OSWC, as measured by OPS, which is a measure of batting skill, he was the best. As measured by win probability added, which is this probabilistic measurement, he was the best. As measured by run production, he was the best. He was just the best, okay? It was a no-brainer. It was an easy choice. This was the right choice. However, before the Dodgers got to the World Series, they played a series that they had to win. And in that series, Tommy Edman was selected as the most valuable player. However, he should not have been selected as most valuable player. Shohei Ohtani should have been selected as, remember that name, Shohei Ohtani? He should have been selected as the most valuable player. His total win credit was more than twice as much as Tommy Edman's. And in fact, as a measure of baseball skill, he was better than Tommy Edman. As a measure of total run production, he was better than Edman. The only place where Edman did better was in this win probability added measure. This is a situation where Tommy Edman, you get more credit, win probability added, places more credit for late inning heroics and for batting in runners than for getting on base. This is the bias in win probability added. And you'll notice that Tommy Edman had a lot of RBI. So this affected his win probability added. Whereas OSWC is not going to bias in favor of RBI over runs. And so it's going to more equally credit those and put them in context for winning the games. By that measure, Ohtani should have won. So Edman, this is a bias we see in MVP voting where they put more weight on run batted in than on runs. In the other series for the Yankees that won their series to make it to the World Series, the award went to Stanton, but Juan Soto should have been the winner. Juan Soto was better in OSWC than Stanton. He was better in OPS than Stanton. He was better than WPA than Stanton. But where was Stanton better? Stanton was better in run production, particularly more runs batted in, but in run production. So in this situation, the award went to the wrong person. So 1 out of 3 awards were right in 2024. This is actually about standard, okay? So this is looking at all the non-pitcher playoff MVP selections. I take out the pitchers because the pitcher is not given for offensive contribution. If the pitcher is awarded the MVP, it's for their pitching, not offensive contribution. So I can't judge whether those are bad choices or not. But for any other player, we can see about a third of the time, the award goes to the person who is the OSWC and the SRC leader. That's an easier choice. That's Freeman winning the World Series MVP correctly. But a lot of other time, the award goes to somebody who shouldn't get it. So this white box is the Edman over Ohtani situation. And this red box is the Stanton over Soto situation. And so what we see in 2024 is basically a replication of the general pattern that voters are biased in favor of run contributions, particularly RBI, and they're biased of win probability added, which is this probabilistic measure of how the change in likelihood that your team wins as a result of your offensive production. Of course, you can change your team's likelihood of winning even though your team loses. That's the problem with that. One of the problems with that measure. It's not actually measuring win contributions. So this is one of the nice lessons from what these data are telling us is that we can look back and see that there's some biases in MVP voting selections. In the future, hopefully, as I promote these statistics, hopefully someday voters will use this statistic when they're making these selections. Okay, and in fact, here's a table. I call these my MVP snubs from the World Series. So these are all the cases where the actual MVP winner in this column was not the leader by OSWC. This is the leader, and this is the difference between the winners, OSWC, and what the person who should have won had. And just 4 years ago, we have one of the worst snubs in history when Mookie Betts from the LA Dodgers was not given the award and it went to a different player. So an interesting situation. So this still happens. Okay, so to conclude, so I've created two new measures of offensive credit. These are grounded in coalitional game theory. They account for credit in a fair way according to these fairness axioms. They're computationally not trivial. Let me emphasize that. But they're super easy to use and interpret. They're just simple shares. So it's really, really easy to interpret. And I argue that the best single holistic measures of offensive credit that exist in baseball now. I've shown you some leaderboards. I've talked about MVP awards. I've shown you some box scores. I have a book that's coming out next year. It's forthcoming where I do more. There's a website. I'll give you the link on the next page. In the future, I'm working on applying the Shapley value to the defensive side. I think I've figured out how to do pitching. I haven't quite figured out how to do fielding on defense. The ultimate goal is to get a unified offensive and defensive win credit. I think that would be that's the ultimate goal. I'm not there yet. Thank you so much. You can go to this website. The website doesn't have most of the technical details. It's mainly meant for a general audience, but the book that's coming out is going to have the technical details on the machine learning and the game theory and all that. So thank you.
Awesome. Thanks, Michael. That was really fascinating and quite a distinct from things we've heard before. So yeah, I really appreciate the detailed, explanation of everything as well. Okay, so I think we'll probably have quite a few questions. We've got a couple in the chat that we could maybe start
Yes.
with.
So how about maybe I can read the question to make sure it gets
Yeah,
on the.
sure. Go ahead. Yeah.
Okay, so first question. Would you consider effort as an element to be credited? That is, effort of performance may not result in desired skill outcome. Okay, so first of all, you're 100% correct that what the player controls is their effort. They don't control the outcome. But what you're proposing is sort of counter to what I'm trying to do. I'm trying to measure what actually happened, not whether the person put in effort. I'm actually trying to measure the actual production. Now, if you tried to do that, what you're proposing is obviously a good thing to try to do. Okay, I'm not saying you shouldn't do it, but I'm saying that that would be a completely different exercise because I'm trying to do accounting for what actually happens in the context. I should say. And you might have this idea in mind when you're thinking about it, because there are other kinds of things players can be doing that are not being credited in this statistic. So let me give you an example. A player that strikes out, okay, and no runners advanced, nothing, they contributed no value to the actual run that scored. However, by making the pitcher throw 12 pitches, the pitcher gets more tired. The next batter sees those pitches, becomes more familiar with the pitcher. That next batter comes up and hits a home run. You could argue that the effort of that first player directly contributed to the outcome of the second player. And my stat is not capturing anything like that. And so there are, but I will say no other stats do either. So, in that idea is something that in reality we think might be there, but we don't really have a way to measure it. I don't think we have great measures of effort, so I think it would be hard to do, but I think it would be a neat thing to do. So I think that's it's an interesting thing. I think it would have to be a different way of capturing it. So hopefully, and feel free to drop in the chat if you think I answered that question sufficiently.
That was a fabulous answer. Thank you so much. I asked that one. My research is focusing on trying to provide more objective structure around what we talk about performance in team sport, field sports. So I appreciated that kind of comparison and the recognition that we really don't have spectacular ways to measure effort. But certainly that it's the example you gave around the home run and perhaps the player before contributing to that is a really great one. So thank you for that answer.
Yeah. Okay. Great. Thank you. Yeah. I agree. So I've coached youth sports for many years, and controlling players' emotions is so important. And especially in baseball and softball, coaching my sons and daughters, they control their effort. I tell them, how do you win? You need skill. We work on that in practice. You need effort. That's what you do. And then there's luck. The ball might bounce one way or another, but these are all three inputs into the outcome. And we just don't have a good measure. We just don't have a good measure of the effort. But it is a crucial element. When I coach, it's a crucial element of the production function. So I'm curious to see how. I'd love to hear more about the work you're pursuing on in this direction. Okay, so next question, Daniel. Comparing between single binary outcomes, run, no run, to more dynamic systems looking at time series data, like contributions to boat speed throughout a race for each seat, would a similar analysis still be applicable? Okay, great question. So I think it's way harder with continuous time. I will say that those efforts to apply, if we think of a difference between soccer and baseball, what makes baseball easier to do the Shapley value with is that the play happens in these discrete chunks. Okay, you have a play, the ball's in play. When that play happens, there's some dynamic stuff, but it's very short-lived. Okay, and then we reset and a new pitch comes. So but the plays can be described as these discrete events more concretely than like in soccer, where you've got players moving all around continuously and the ball's in one place and the defenders are all over. The way that they tried to apply the Shapley value in soccer was by using estimated goals as the value, okay, not actual goals. And so they tried to smooth over the continuity in this way. But that means they're doing something totally different from what I'm doing, because I am trying to assign credit for actual runs, for actual win, like not expected runs. That's what win probability added is trying to do, expected runs. Now, but that one application in soccer that's been done, they had expected runs, and they tried to figure out what the value of different coalitions in generating expected goals. Now, but I think it's a much harder problem to solve. I don't really have great insight into like any key innovation there. But to be honest, I haven't really tried to tackle it. I thought baseball was hard enough. So unfortunately, Daniel, I don't think I kind of have to punt on that one. I think that's a much harder problem. I don't know, Daniel, if you want to comment on that.
Yeah, no worries. No, as I was hearing your talk, I was just thinking right away about like seat selection, for example. When we've got different boat classes, different boat types, and we get a lot of time series information on these athletes as they're, training or competing throughout a piece. But I'm not surprised that it's a little bit a bit of a rabbit hole. So
Yeah.
no, I really appreciate it. The talk was fascinating. So thank you for the input. Hoping to interact with some of this at some point in time within that space.
Great. Yeah, thank you. Yeah, this is another feature of this is because I'm using this concept from coalitional game theory. So coalitional game theory is one branch of larger game theory, but it's a branch of game theory where players are assumed to work collaboratively, not sort of selfishly. And there are certain rigid structures of the way you formalize and represent a coalitional game that the Shapley value takes advantage of. So if you given this structure, so I can like go back here. It forces you, coalitional game theory requires you to construct this value function. Okay, you can't, like if you don't have this, you don't have a properly defined coalitional game. This is a very rigid structure. And so, when you think about a continuous game, it's harder to imagine what sub-coalitions look like. What does it look like on the soccer pitch when you have 2 out of the 11 players or something? How do you envision what the value, how do you envision what those 2 players can do? That's kind of, yeah, it's same thing in basketball, I would say, same thing in hockey. All of these like invasion sports where the movement is so fluid. I think it's harder. I don't know if the Shapley value would be the best way to do that. Although maybe there's some innovation here, for some future researcher to figure out a way to to do it.
I have a question. So you showed a very tight correlation with weighted runs participated in. So,
Yes.
and you also made a very eloquent, speech about how to, your statistics should be used. But this would suggest that, what's the added value of SRC,
Yeah.
over, and how do these two statistics differ
This
in their
Great.
computation?
Oh, wow. Good one. Okay. So this is not a statistic that I created this as
Okay.
a sort of shadow. So in the baseball sabermetrics, there's this term that some people have used called a shadow stat. Um, a shadow stat basically is like a very, very simple stat we know is wrong, but is much easier to calculate and is really is pretty close to the best one. Okay. And I created this one. So there was an RPI stat, which is really quite a bad stat, so no one uses it. I created a weighted version of it, and I actually show that the correlation with SRC is pretty tight. This though is season SRC. So over the course of many games, the correlation between SRC and WRPI is super, super tight. And this is simply half of your runs plus half of your RBI. It's really simple. But the problem with this is this correlation is only tight if it's for season SRC and season WRPI. So in any given game, these two are going to vary a lot. So if you look at this box score, okay, so Rojas's WRPI would be 0.5 because it's half of this plus half of this. So this would be 0.5, but really it should be 0.33. This guy, Marte, should be 0.5, but it's 0.83. This one should be 0.5, and it is. And this guy should be 1, but the WRPI would be 1, but really the truth is 1.33. So within the small sample, WRPI is not very good. But averaging over a season, WRPI is actually amazingly good. The idea is that really, I explain, really, it's not that you should get half credit for every run and half credit for every RBI. Basically, what you should get is you should get half credit. You should get about a third credit for every run, about a third credit for every RBI. And then there's about a third credit you should be getting for all the times you do things that help your teammates score, but for which you're not given a run or RBI. But it turns out that we can proxy what that third category is, which isn't measured in the data. We can proxy for it by runs and RBI. And so if we use that as an RBI, we end up weighting half on runs, half on RBI. And so it's you can argue on behalf of this weighted runs participated in statistic using this kind of argument about coalitional participation. And it just turns out to be this really simple calculation. But yeah, it's not good for a WRPI would not be good for it wouldn't be quite as good for this when you're looking at within a series. It's gonna differ because it's smoothing over a lot of things.
Gotcha. For the leaderboards, what is the effect of like the season duration, so the number of games per season, or someone's career span in contributing to these statistics?
Yeah, so good question. So these are SRC and OSWC are counting stats. And so they are going to benefit players that play in more games and played in seasons where more games were played are going to have more opportunities to get the stats. And that's another reason why you don't really want to use this stat as a measure of a player's skill, because it's a counting stat and it's based a lot on opportunities. Not only of course, it's correlated with your skill, okay? Because if you're a better player, you're going to play more, okay? So it is correlated with skill. It should be correlated with skill, but it's not a precise measure of skill. Moreover, it's also because it's based on collaboration, your SRC and your OSWC will depend on how your players played. So if you are So let's look at Shohei Ohtani and Aaron Judge. These were great players. They were just had incredible seasons. But the fact that Shohei Ohtani could contribute to this many runs, it would be a lot lower if he were not on a good team. These two players were also on the teams that had the two best records well, the Dodgers had the best record in the National League. The Yankees had the best record in the American League. And so it's not a surprise that they're leading the way here. But this is their share of team production. That's the thing. So it's not individual skill. It's their share of team production, and it will depend on the team. OSWC even more so, because on the website, I look into this. I show that, if you're on a better team, there's two things that could happen. And Bill James, an early sabermetrician, baseball analyst, made this argument. And he conjectured one thing that I show is wrong for my statistic. He said, if you're on a good team, then there's more good players. And so if you're dividing credit for the wins, you're dividing pie among more people, so you're going to get less. But as a better player, you should get more. And he argued that in the end, those two things wash out. And so that the win credit statistic shouldn't really depend in the end on the quality of the team. I show for my statistic that's not true. If you're on a better team, you're going to have more opportunities to win, and that is going to outweigh the fact that you have more good players you're going to have to split the credit with. And so all of these players, they're not just really good players. These teams they're all among the best teams. And so again, it's not a great measure of player skill. It's just accounting, and the better team is going to have more credit to split among its players.
Great. Thank you for that. Okay. Other questions? Okay. Well, we got one from Dr. LeBlanc. Please unmute and go ahead.
All right. Thank you. Thank you for the talk. It was super interesting. The first thing that came to mind when you went through this example where the wrong winners were selected, at the end of the season, I wondered what the role maybe of the losses would have been in there. Like I can see that for this, the OSWC, they're not accounted for at all. But did I miss something? Is SRC actually still including the losses? And if not, yes, that obviously will contribute more statistics and more runs scored and batted in and everything.
Yeah, good catch. So this is a key feature of OSWC. You're only going to get OSWC if your team wins, because you only won when you win, right? So, but SRC is for the entire series. That includes the losses. All of these numbers over here, this whole part of the table, this is all wins and losses, the total. So this is the total SRC for the whole series. And so what you see in a lot of these cases where the award goes to someone, it turns out it's someone who played really well when the team lost. And so you might say, oh, but they were still a good player. And then I would say, well, sure, but you can imagine a scenario. What's more valuable? Suppose I hit a home run and my team wins 1-0. That's really valuable. Suppose I hit a home run and my team loses 10-1. It didn't help the team win. It was great. It's a manifestation of skill. It produced the same number of runs as my other home run, but it didn't have any win value because it literally didn't help the team win. And so this OSWC is saying we're only crediting for the contributions that actually help the team win. I'm not saying that other contributions weren't impressive. What I'm saying is they didn't produce wins. And so which were the contributions that produced the wins? If you go back a little bit, you can think, actually, this kind of logic, at first this might strike it might sound a little funny because it seems, well, this is still a good player, and that the outcomes they achieved in the losses should still be accounted for. That's fine. You can make that argument. I would argue then you are not assigning the value based on winning if you want to do that, which is fine if you want to do that. But I would argue that's not assigning value for winning. And so in fact that can happen. You can get so if you hit a home run to start the game off and your team goes ahead 1-0, you would get a large boost in WPA. But then if your team actually loses, you helped your team increase their chance of winning, but they didn't actually win. So you're getting an imaginary boost in your win value. So I argue that it's actually, the contributions to the wins that should count for the MVP award. It makes sense if you think about it differently. So in baseball, if you have someone who hits a double to lead off an inning, but they don't score, they didn't help their team score, even though it was a great hit. Later, someone hits a double and they score someone. Which double was more valuable? The one that actually scored someone. And so the value is really context specific. It's not measuring the skill. It's just in the context which contribution was most valuable. So anyway, that's the sort of philosophical argument for the fact that in the OSWC statistic, why the contributions and the losses are not counted, but those are counted in the SRC. Hopefully that certainly people can disagree philosophically on this, but that's the argument I give.
Sure, no, that totally makes sense. But then I was thinking of something along the lines of like clutch batting. It's not. This is a little different, definitely. Clutch batting in a win is not the same as clutch batting in a loss, for one thing.
That's right.
I mean, we'd have to argue with that, agree with that, sorry. But something like, you were given this example of a home run that will make you win, as opposed to one you're losing 10-0 and then you hit a home run. Well, we could argue that if they were behind by one and you hit a home run in the ninth inning, even though you end up losing in extra innings, that had a lot of value. But this does not capture it, which is fine. I mean, we have to understand that we're different. We're measuring different things, obviously.
Yeah, that's right. And that one you're talking about is literally what WPA is capturing.
Great.
So like if you get a late inning home run, say the score is tied and you hit a late inning home run, you're going to get a huge WPA. And then your team might come back and lose the game. Well, you still have that WPA because you already accumulated it. And so WPA is capturing exactly it's one I should say it's one way
way
of capturing that. And some people argue that WPA is one of the best measures you should use for selecting the MVP. And it's a different argument. So I'm going to argue that it's a flawed one, but this is not like there's only one right answer. I think when it comes to MVP voting, one thing is clear: people have to choose the standard that they use, and I certainly have an interest at stake. I want people to use mine, so I'm gonna take out a pretty strong position. But we're all friends in the end, and I certainly what WPA captures is the emotion. Because when you see it, and that's what's so memorable and why WP I think is so valuable to the voters or the selectors of the MVP is because it really captures like the emotional experience of the game. Like a high WPA event was like very dramatic. And so and we think that and there's also this idea I think in the voters that players that perform in these high pressure situations should be given some sort of additional merit. Because of that. And that's why the player that bats in the batter. So if you have two players who hit doubles back to back, so one player gets a double and they get on base, and the next player gets a double and they score the first player. That's why we tend to value the second batter, even though they both did literally the same hit. We value the second batter because he's the one that finished it. He's the one that brought them home. And WPA is going to do that. It's going to value that second second batter more, and it's going to put more credit in late innings.
All right, thanks. That's extremely clear. Thanks very much.
Okay, great.
All right, everyone. So we are at 11:15, and Dr. McBride has answered a lot of questions, so which we really appreciate. So I'm going to stop the recording here. Before I do, I just want to thank Michael one more time for a great talk. So thanks again. And yeah, we'll just be around for a couple of minutes of informal chatting if you want to stick around. Otherwise, we will see you in a couple of weeks. Thanks, everyone.
Yeah, thank you so much. Thanks everyone for coming.